Okay. No, okay. Okay, welcome class. Maybe there. I tried to improve my life by having an external microphone, but I have no clue if it actually was working. And I would appreciate if somebody could just start up the live stream and see if the audio is coming through. It looks like it's coming through, but I'm not totally sure. Okay, let me check if the recording has streaming running, recording running. So yeah, and people who are out, not in the room but in the live stream, and they experience a problem, please send a message to one of your friends or.
They say it works.
Great, yeah, and because the idea is now with this clip-on microphone that the sound should be better and that I'm not obstructing with my papers the I'm trying to improve my life. Okay, today's topic, Lagrange equations of motion, and actually you already know the topic, so these 2 hours are totally wasted time. Probably not, because I'm going to, of course, the end result, Lagrange equation of motion, is the same as you had experienced using the advanced dynamics class. However, the way in which we derive the equations, and on top of that, where we show how to add active and passive elements and do impact calculations, that is on top of the advanced dynamics Lagrange equations you learned. So it enlarges a little bit the topic. And well, I like Lagrange, so I like to talk a little bit about the guy. But before we do that, let's see how you are within your knowledge of last lectures and of course advanced dynamics, if you still know what Lagrange equations are. So let's move to the Kahoot quiz. Yeah, I can do that. My Kahoot. Yeah. Number 5. Classic. Oh, yeah. So we're aiming for 176 participants, plus or take 1. $155. Oh, there maybe people are still returning from skiing holidays or going on skiing winter sport things. Or yeah, that's a yeah. Where is it? Come on, get real. Oké. Nee, die blijft er. Ja. Okay, well, it seems like to stabilize. Let's start the quiz. Again, 5 questions and 90 seconds with a 10-second delay in the stream. This is a golden oldie, right? So it's exactly the same question as last week. Please discuss, eh?
Ja, maar... Ja.
Yeah, okay, pretty good. So I have nothing to add to that. Next question. The constraint force Fx, Fy is... So the live stream people should speed up. So yes, this is a nice feedback question on your knowledge. I'm not going to explain now because it's actually in the book, the example. So for those who do not have the correct answer, just study the example in the book. Yeah? Okay, we move on. Is Price in the room? Great. The Lagrange equation of motions are no. It's only look at the pluses and minuses and the i's and the j's and the. And the dots and no dots.
Oh ja, ja, tuurlijk. Ja. Maar is dat... Ja.
Yeah. Okay, super. Okay, this, I think it wasn't so hard. Ah, you lost it. Karan? Yeah, of course. Good. Potential energy. What is the definition actually?
Ja, mooi, ja.
Let me look where what the answer number one was. Oh yeah. So it looks like there's a competition between two answers, between 1 and 2, right? So 43 were for 1 and 94 for 2. Most of them are correct, of course, but it's interesting for these people. Yeah, the definition of potential energy is a bit awkward. So it is the force not in the same direction as the displacement, but in the opposite direction. And it all has to do with that the energy you are calculating is a sort of energy storage. And I always find the easiest way to remember it is if you take a point mass, and then the force is always down, right? Because Earth is here somewhere, so it's pulling. So it's in that direction. But the higher you put it, that we say, oh yeah, the potential energy is higher. Yeah. So the displacement and the force are in opposite direction. And that's the only thing you have to remember. Yeah? Very simple. Okay, ready for the last question? Carry on, good. So this is really today's topic, generalized coordinates.
Okay, dus dan was je dat
Je weet ook. Ja, sorry, mag ik ook? Echt niet te zeggen is. Dat zou ook niet zijn.
Yeah, no question about that. Okay. Good work, Karam. Yeah, feedback is always appreciated. Thank you. Okay, then we can stop this one. We can stop this one. This one is still running. That's good to see. I see my noise. Yeah, okay. Okay. So today's topic, as I said, is Lagrange equations of motion. Let's revisit until now the equations of motion we derived. So our equation of motion for our constrained system, we're always coming back to the following set of equations. We had some mass matrix, then we had some Jacobian of the constraints, then we had these accelerations of the center of mass, we had the Lagrangian multipliers, and then on the right hand side, of course, we had the applied forces, and there were some convective terms, or minus C2 x dot, something like that. I don't know how to write that, but it's just a vector with stuff. So, anyway, now there's something wrong with the sound of the live stream, really. Let me see, something wrong. I have super audio here. Maybe because I put my papers there, I don't know. Looks good. Oh, it's better. Oh, yeah, still. So apparently the mic isn't working, but my laptop. Oh, thank you. We continue. Much appreciated. Where are we? Here. Yeah. So now, imagine that you have many bodies, like here in the room, many bodies, meaning that this part, n, is large. Oh, that's not nice, large. But also that you have many constraints. So many constraints, meaning and we indicated the number of constraints by mic, by the letter m, so m is also large. That means that the system of equations you then get is also large. So the system of equations, which is in total this n plus m, is large. So you have a large set. Whereas the degrees of freedom, how many do we have for such a system?
Minus m?
Yeah, n minus m. So n minus m, although n is large and m is large, n minus m can be small. And then the idea is, of course, are we not able to, instead of writing our equations of motion within this large set of coordinates for the rigid bodies, together with all these constraints, why don't we identify a number of coordinates where we say, oh, these coordinates can describe the motion of the system. And those motions, those coordinates we call generalized coordinates. Generalized coordinates. So that's when we move from that to that small set, in n minus m in total, or the degrees of freedom we take. So that is the concept for today, generalized coordinates. Now, what are generalized coordinates? I have an example. Of a generalized coordinate, and that is 52. What is it? Oh, point. Sorry. 1,4.36. This is an example of a generalized coordinate, right? Can anybody tell me what it is?
GPS?
It's not a GPS. The latitude and the longitudes. Very good. Yes, it is here. This, where I'm sitting. It's my coordinate on the globe. Now, why do I say so? This is latitude, right? Latitude, and this is longitude. So actually, it's a location on the globe. So if you sketch the Earth, and this is Earth, something like this, with all these lines on it, and then somewhere on the Earth, I am standing here. And that point on the Earth is given by these two coordinates. Now, the words latitude and longitude in itself are very interesting. So that it's Earth, I always like to say the omega is 1 RPD, right? 1 round per day, which in radians, what is it in radians per second? A very low number. Something like 7, 10 to the minus 5 radians per second. Very low rotational speed. Okay, so we are constrained to move on this Earth surface, right? And so if you would draw that in a mechanical sense or in a kinematic sense, then we would say, oh yeah, I have a surface here, and I can only move on this surface. Yeah, that is what we are doing here. And what are latitude and longitude? Well, if you take some coordinate system at the center of the Earth and you take some zero line, then it's two angles. One angle is this one, so this is what we call the longitude angle, and the other angle, that is from the horizon, from the zero meridian up, zero equator line up, that is what we call the latitude. Now, latitude is not so clear to me. With latitude, I think of latte or milk, but so I have no clue where that came from. But longitude, long, that's like a length. However, if you look at Earth, I mean, wherever you are on Earth, every direction is as long as any other direction. I mean, wherever you're standing, the globe is long in every dimension. I mean, there is no preferred direction, right? So where does the name longitude come from? Does anybody know?
Same length.
Sorry?
Those lines are the same length. Circumference.
Those are the same length? Any circle I draw on the globe. Oh, okay. Oh, yeah, that one. Yeah, but if it go higher, they become shorter. I mean. Any other ideas?
Can you repeat the question?
So where does the name longitude come from? Because a globe, in which direction is a globe long? I mean, if I have a pen, then this is the longer side and this is the shorter side. So if we call a coordinate on the pen this the longitude and then the other one the latitude, I can imagine. That's clear to me. But now we take a globe, my head. Everywhere on the globe, I mean, every direction has the same dimension, so where does longitude come from? Well, the answer is you have to go back to the first navigators. I mean, those were the people who had to know distance on the Earth, because they had to move from A to B, and being on a sea, you have no hooks whatsoever. Yeah, you have the stars and the heavenly spheres, but they still didn't have an exact clue how those moved. So the moment you were in the middle of a sea and you had no points, you were sort of in trouble. So they had to navigate, and in navigation, you need coordinates and you need magnetic and distance and so on. Now, and where did the first navigators navigate? Well, of course, they didn't go to the Atlantic Ocean, right? Because that's super scary, because there's an edge, and if you go beyond the edge, you just fall off. So don't go there. Don't go where all those, where not the lions, where the dragons are. Don't go where the dragons are. So where were they? They were trying their whole navigation skills on a smaller sea. Now, and what is a smaller sea? That is, of course, the Mediterranean, right? Something like this, and then we have Greece and some other countries, and blah, 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 blah. And we have Africa and Algeria, and Morocco, and so on. So, if you are in the Mediterranean, there's a small island here, and here's also one, and here there are a lot of islands. So, in the Mediterranean Sea, this is of course the length of the sea, right? So, therefore we call that longitude. Okay, nice interlude. Let's continue with generalized coordinates. Let's take an example, and I draw here a 4-bar mechanism with a roller. And then the first question, so the sticks are rigid bodies, so if I do it right, I should draw it really like this. And then enumerate that, 1, 2, 3, so we have 3 rigid bodies. Number of connections and the number of constraints. Now, how many degrees of freedom do we have for this system? 1, 2, 1. I like to have consensus. 4, 2. Okay, let's vote. Who votes for 1? Okay. Who votes for 2? That's a lot more. Who votes for 3? Nobody. So you. Yeah, but you first at 4, but you just subtract 1. Okay, and more than 3? Oh, no, I don't think so. No, the majority says 2, so it's 2 degrees of freedom. So it's easy, right? Well, actually, you want to know, is it correct or not? I mean, democracy sort of sucks in a sense. Because, okay, then we say democracy tells us 2, but then still we don't know if it's really true, right? So, how do we do that? Very simple, by calculating. And I had a simple rule. I have 3 rigid bodies, and every rigid body has 3 degrees of freedom. So, in total, I have 9 degrees of freedom as free bodies. And then I just count constraints. I have a 1, 2, 3 hinges with the rigid bodies connected. So 3 hinges times 2 is and I should put a minus, minus 6. And then of course I have here a rolling constraint, meaning that the point is not completely free, it is confined to move horizontal. So I throw away one, or I add one constraint, or as you like it. So minus 1. So then the outcome is 2, and yeah, that complies. So now we have a sort of a better feeling than this voting. The next step is, of course, if you want to use generalized coordinates, you're actually free to choose whatever you like. So let's draw some coordinates in the figure. And an obvious one is, of course, to say, oh, I have this distance s, and I have this angle alpha, but I also have an angle here, beta, and maybe this intermediate angle, gamma, is also interesting, or maybe the absolute angle of this one, delta. So you can, or the height of this point is also maybe an interesting one, y. Now let's call it h. That's so stupid. H. So candidates, you could say candidates for those generalized coordinates, GCs, are yeah, the one I wrote here, the S. That's not a nice S. What happened there? S. S, alpha, beta, gamma, delta, H. And then, so I just name a few. I mean, you can take whatever you want. You could even think, or you could do alpha plus H. Why not? I mean, it's a generalized coordinate. If you like to do that, that's fine by me. I have no problem with that. Or you can take gamma divided by alpha plus beta. If you think that's a nice coordinate to use in my system, no problem. That's the whole concept of generalized. However, in this case, what would be a proper choice? And with proper, I mean useful, handy, not too complicated. Any ideas? So we have to take two out of the whole list. And choice is with this? No, with this, right? Proper choice. Whatever, choice.
Alpha and S.
Alpha and S. Okay, any other ideas? Alpha, beta. Any others? S and beta, yeah. S and H. One of the top scorers in the IQ is doing like this. So maybe there's something wrong with S and H.
I agree.
But no, I agree. S and H is maybe not such a smart choice. What is the problem with S and H? Yeah, exactly. S and H has a problem because so if you choose S and H as generalized coordinates, then if you have to draw the mechanism for some certain H and a certain S here, then this is a solution, but this is also a solution. Oh yeah, and I should put this one then, because this stays here. So, meaning that we have two sets of configurations, x, y, who both map to one set of generalized coordinates. So, if you put here the space, and everybody in his middle school learned about all these diagrams, right, with the verzamelingen. I don't know, what is it called in English? Sets. So set theory. So you have a set, and this is the set of all the center of mass coordinates, and this is the set of the generalized coordinates, and so these are generalized coordinates, and these are the CM coordinates. Then what we have in the picture on the left is actually that we have one set of generalized coordinates, and 2 points within this set are mapped to the same set of generalized coordinates. So I'll put the direction arrow here, then it's better to see. So going down from, given a configuration, what are my generalized coordinates, that works perfect. But the other way around doesn't work. So if you say these are the generalized coordinates, then oh yeah, either you go to this mechanism or to this mechanism. And you could say that is sort of like a bifurcation in the whole thing, and there's a whole theory around it, but I shouldn't do that. That makes life too complex. So it's nice to have a nice continuous function and a unique one. So this is what we say non-unique, actually. Non-unique GCs, generalized coordinates. But you're free to make your choice in the generalized coordinates, so you can always find a set which sort of works for you. And sometimes if you stay only in a local region, like if you only live at Delft and so on, well, what do you have to know about navigating on Earth? I mean, going back and forth and left and right is more than enough, right? So also within this whole system, the choice is demanded by the application. Okay, let's go to Lagrange, because that is the topic of today. In 1788, he wrote a book, and it's called Mécanique Analytique. And I like to share with you actually the advertisement he makes for the book. So I have the book here somewhere. Here we are. Smaller, don't kill it, yeah. Where do I have the book? Course, which course, this year, this lecture. Yeah, so this is his book, Mécanique Analytique. And as you can see, par Monsieur de Lagrange, and it's interesting to see that you would say, oh, he couldn't even write his own name. But it was very common to spell names in different manners. People didn't really bother with that. Académie des Sciences de Paris, that's why it's of course in French, but they also have a dépendance in Berlin, Petersburg and Torino. Well, now he also worked in Berlin, Petersburg and Torino. He's actually from Torino, so he's in Italian. Lagrange is in Italian, no doubt about it. Of course, the French claim him as a French mathematician, but he's not. He's Italian. And then here there's a puzzle to find out when the book was published, right? Nice puzzle. Oh, I already gave the answers. 1788, right? Yeah. Okay, so let's continue. Avertissement. So this is so if you are in a shop and you want to buy a book, then you read the abstract or the introduction or the advertisement. Please buy my book because. Now, and here it comes. Avertissement. On a déjà plusieurs traités de mécanique, mais le plan de celui-ci est entièrement neuf. Well, I think most of you who cannot understand French. Oh yeah, me too. I have also trouble. But I mean, you can bluff your way through it. It's not so hard. If you know a little bit Latin and Spanish and you listen to songs on the radio and then, who knows. On a déjà plusieurs traités mécaniques. There are already a lot of books on mechanics, he says. Mais le plan de celui-ci est entièrement neuf. But the book I show you here, or the plan, the method I show you here, is totally new. So he says, there are already a lot of books, but my book is new, what I'm going to show you. Je me suis proposé de réduire la théorie de cette science et l'art de résoudre et le problème qui se rapporte à la formule générale. Well, there's a lot of humbug words, but it's about science. It's founded on science, and he will show you a method by which you can solve in a general way all the problems. And then a lot of more French. What does he say? Le simple développement donne toutes les équations nécessaires pour la solution de chaque problème. I gave you all the formulas by which you can solve the problem. So it's like you're following a course and they give you a book and say, here is all the solutions. Good luck. En dan j'espère que la manière dont le pub rien à décider. I don't know what he's saying. And then he goes on where you can apply that. Not so interesting. He says, I divided, je le divide à deux parties. Ja, okay. La statique et la théorie de l'équilibre, so statics, et la dynamique ou la théorie de mouvement. Oh, statics and dynamics, right? French isn't so hard. Yeah, and then also a little part on the corps solide and the fluide, so a little bit on rigid bodies and also fluids. But now comes the apotheose of the advertisement, because he says, and this is an important part, on ne trouvera point de figure dans cet ouvrage. So he says, here is a book and there are no figures in the book. So this should be an advertisement to buy the book, right? But whereas, what is a book without pictures and conversations, says Alice. I mean, Alice in Wonderland. A book without pictures is nothing. We don't want books without pictures. Nevertheless, Lagrange says, as an advertisement for his book, on ne trouvera point de figure dans cet ouvrage. You will find no figures will be found in this book. Okay, let's read on. Les méthodes que j'ai exposées ne demandent ni construction. So the method I show you does not need any construction. So construction meaning with a ruler and a pen and a line. Ni raisonnement géométrique ou mécanique. So no mechanical reasoning or geometrical reasoning. You don't need that. Now, why does he say that? Have you read Newton? No? Oh, you should have. I mean, I gave you the piece on the impact. If you read that part, you see that the reasoning he does is purely geometric. He says, I have two balls and they collide and one goes high like this and the other like that, and in relation to this goes to that, and in ratio to this is a ratio to that, and everything is with ratios and compared to. But now comes Lagrange and he says, we're not going to do that. You don't need it. Mais seulement des opérations de algébrique. So the only thing you need is algebra. So if you're good at doing algebra, then you're in business. You can you can derive the equation of motion for your mechanical system. Ajouter à une marche régulière et uniforme. So algebra in a regular and normal format. We don't do higher algebra. We don't do imaginary numbers or those kind of things. Everything stays within the real world. Very simple algebra. And then the next sentence is ceux qui aiment l'analyse, for those who aiment, love or enjoy the analysis, verront avec plaisir la mécanique. So will do mechanics with pleasure. Et devenir à une nouvelle branche et me feront avoir attendre à le domaine. And in short, he says, and by this book I have added a new thing within the field. So he makes an enormous leap from geometrical reasoning to algebra. Yeah? No figures in the book. And if you check the book, and there's a nice English translation here in the library, indeed, there are no figures. It's only text and formulas, and that's it. And that's about mechanics. Okay. That was what I wanted to share with you about Lagrange. Yeah. Let's go back to those equations now. So the bottom line is change this a bit. The bottom line is that Lagrange rationalizes the whole mechanics, and instead of looking with geometry and ratios, he now uses algebra. And in doing that, he uses a concept which we call energy. So energy is the basic thing which Lagrange uses, and then energy is what we call, until now we haven't really talked about energy, but it's power times time. to connect that. So that's energy. And the power was in watts, and watts times second, and then you get joules. To get the units right. Now, power is a very of energy, and power is a very general thing. We are looking at mechaniek analytiek, so we're looking at mechanics. So we're going to look at mechanical power. So for mechanical power, and then just take the one-dimensional case for simplicity now. So I have a force and I have a mass at a location. So I have a distance, I have some mass, and I have an applied force. And then how does it go? Well, power then is defined as force times velocity. Super simple. And then of course energy, so this is what we call power. And then energy is of course the sum over time of that, so that's the integral of power with time. So in our case that is then the integral of the force with time. Now, since we were going to do mechanics, we need some, what I always say, mechanical constitutive law. So we have Newton, and Newton says that the force is the mass times the acceleration. Now this is a Newtonian equation of motion. Now I'm going to transform it to an energy equation. And how do I do that? Well, to go to energy, then first I have to multiply, of course, with speed, because what did we say? Energy is power over time, times time. So first I have to get power. So then we do force times velocity and then here mass, velocity. And then to get energy I have to integrate both sides with respect to time. And now I have my energy equation for this one-dimensional case. You can simplify the integrals a little bit, because x dot by definition is x dot dx dt. So I get f dx dt times dt equals, and on the right hand side I get m. Well, x double dot I can write of course as dx dot dt, that's the acceleration, times x dot times dt. So now I cross out these dt's, so I'm going to change my boundaries of integration. And then finally I get my energy equation, and the energy equation for this one-dimensional case, that the integral of the force times the distance, or the increment in this is equal to the integral of the mass times the velocity times dx dot. Now let's take a very simple case. So, and the most simple case for f is constant, a constant force, some value. Then the integral of f dx just breaks down to f x2 minus x1 equals, and then on the right hand side, well, if we integrate this part, we get 1/2 m x dot squared, and the only way to check that is to differentiate that. And then of course the boundaries between two boundaries. Well, it should be 1/2. This is what we call the energy equation. And if we then give terms a name, if we say T is this 1/2 mx dot squared is what we call kinetic energy, because that's something like the mass and the velocity, the kinetics of the thing. And if we call potential energy minus force times distance, here is the quiz again, then you can recast the equation and say, oh, apparently the kinetic energy plus the potential energy should be constant. And that's what we call energy conservation in the system. If you have non-dissipative forces, this was for conservative forces, if you have non-dissipative forces, then the energy you put in, mechanical energy, force times distance, is then transferred to kinetic energy, that the thing is going faster. Or if you push the other way, that the thing is slowing down. That's how things go. Okay, let's do a break, and then after the break we continue. Yeah, let me stop and save something. Stop the recording and